All right, we are recording. So good morning. Today we're going to finish our introduction to vectors, and then probably we'll get into the dot product, a way of combining two vectors to produce a scalar, and that scalar actually tells us something interesting about the original two vectors. And then subsequent to the dot product, next week we will get into the cross product, which is another way to combine two vectors, again, which produces a result. In this case, it produces another vector that tells us something about the original two vectors. All right, so let's get into the next example. We finished last day with a discussion about two-dimensional vectors and finding, in this case, it was finding the vector that went from the tip of R to the tip of S. So this was 2 points in space, R and S, and we wanted to find the vector that went between them. And we did that, and the way we ended up doing that was we said, if we want to go from R to S, so in this picture, I'll just highlight it here, we wanted to go from point R to point S, then what we did was we took the coordinates of the tip, which was -5 and 4, and we subtracted from the coordinates of the tip the coordinates of the tail, and the tail of that vector is the coordinates of R, which was 5 and 10. So often referred to as tip minus tail. If you want to find a vector between 2 points, you take the point that represents the tip and the point that represents the tail, and you take their difference, and that gives you the vector between them. So we're going to apply that same technique to this next problem. Now in this case, we're in 3 dimensions. So we have a vector, we want to find a vector v with coordinates a, b, c that goes from, in this case, R to S. So that notation tells me that I want a vector. That's the arrow on top of the juxtaposed point names. So we've got a vector symbol above it telling us we want a vector, and it's going to go from R to S. So the order matters there. So let's figure out where R and S are in space. So go ahead and we'll draw our coordinate system. And this is X and Y, and there's positive Z pointing up. So what are our points? Our first point is R, 5, 1, 10. So we're 5 units along the X direction. We are 1 unit along the Y direction, and we are 10 units along the Z direction. I'll just notch it out like that. Okay, so we've got our distances along each of the axes that we are. Now we have to figure out where that point is, and I like to draw these rectangular boxes to just give us a feel for where these points actually are. So let's continue drawing these boxes here. So it's going to go like that, like that. This one's going to come down. Okay, so I've drawn a little rectangular box there. And the point we're interested in is right here. I'm just going to move that 5 over because it's a little too close to the point and it might be distracting. So 5 is the height up the y-axis. That's what, or up the z-axis, sorry. So there's our first point, R. It's, now we can see from this sort of rectangular box drawn, it's 5 units along the x direction, 1 along the y, and 10 along the z direction. The next point is 0, 5, -10. So we're 0 units along the x direction. And so everything's happening, 0, 5, -10. Maybe I didn't say the negative, but -10. So then we're 5 units along the y direction. So there's 1, 2, 3, 4, 5. And we're -10 units down the z-axis. So there is -5, and here is -10. And so I'll draw our In this case, our rectangular box is really just a rectangle because it's living in the YZ plane. The point lives in the YZ plane. Its x coordinate is 0. So the point is sitting right there at the bottom right-hand corner. And so that's S. And the vector we're looking for is the vector that starts at R and goes to S. So that's the one we're looking for. Starts at R and goes to S. So let's call that vector V. And the way we get it is, now I'll write this down, but it's in some sense what I'm about to write down doesn't really make sense, but I'm going to write it down in parentheses. So, well, maybe I'll write it off to this side. What we're thinking here is that it is really the tip minus the tail, so it's R minus S. That's what we're thinking, R minus S. But these are points. R is a point and S is a point. And there's no operation of subtraction or addition of points. We only have operations of addition or subtraction of vectors. So instead of thinking of it as the point R minus the point S, we could think of it as the vector R, 5, 1, 10, minus the vector S, 0, 5, negative 10. So that's sort of our tip minus tail. And again, this R minus S, this is not part of the calculation. This is just what we're thinking, tip minus tail. So I'll write that here, tip minus tail. Okay, so this is 5 minus 0, 1 minus 5, and 10 minus 10. And so our vector is 5, negative 4, and 20. So that's our vector V drawn. Okay, and now the last part of the question says sketch both the vector R to S, which we've done, that's our vector V, and the position vector of the point P, which has the coordinates given by A, B, and C, which are the components of our vector. In other words, we're going to slide that vector V so it starts at the origin. And so it's got to go 5 units along the x direction. So I'm going to put this in a slightly different color. It's 5 units along the x direction, negative 4 units along the y direction.
Excuse me, is that tip
yeah.
R or S?
Sorry, did I get this wrong here? Tip is, oh, S, thank you. Yes, I did get it wrong. Thank you. Tip minus tail. Tip is S. Tail is R. And I wrote these ones down wrong here. Okay, thank you. Let me cancel these out. We have, yeah, I was going to say, I was like, well, we shouldn't be going in the negative y direction because our picture looks like we're going in the positive y direction. So this is, thank you, 0, 5, negative 10, minus 5, 1, 10. And I'll cancel that one out. And for this one, the answer is really just negative what I've written down here. So I set the 2 negative signs in front. So that looks to be a bit better. It's going in the negative x direction from our picture, in the positive y direction, so off to the right, and in the negative z direction down. Yeah, so that looks better. Thanks. Thanks for catching that. Okay, so now we're going to be negative 5 in the x direction, 1, 2, 3, 4, 5. So out here, negative 5, 4 in the y direction. So I'll just sketch these 2 things in there. That's 4. So it's going to be along a vertical line that passes through that point. And it's negative 20 down. Well, that's going to be quite a ways down here. I'll just sort of cheat a little bit and not make it go as far. And so we've got to actually get our perspective right. So this is going to be negative 20. So we're going to come something like this. Get rid of that part there. Okay, so I'm going to highlight this box in a different color just so we can see it a little bit more clearly. Put it in a gray. get the rest of the box sort of drawn in the background here, something like this. Fix it so it actually looks like a box. Okay, so there's our rectangular box, and the vector, let me get the right one drawn here. The vector is going to go from the origin to -5, 4, and -20. So let's get that in here. So I've got it at -20 right there. So you may look at that point that I'm highlighting and go, that doesn't look like it's at -20, but we have to look at the perspective of the drawing. This entire plane is at z value -20. And so we're picking the point on that plane that's sitting directly below the point -5, 4 in the xy coordinates. So directly below this point up here at the top. So got this line coming down to our point. And so that's the vector we're interested in. That's this one here, starting from the origin and going off. So that gray one is our position vector. Okay, so we can see that, drawing these things in 3 dimensions, it can become somewhat challenging to make sure that we incorporate all the necessary information so we can actually figure out what the x, y, and z values are of the points and be able to read them off. And this is just due to the nature of we're trying to take this 3 dimensions of information and pack it into a 2-dimensional plane. So we need some perspective lines to get that happening. As I said last class, it's a good idea to accompany any of your your work when you're studying at home with some visual tools to help you picture these things. So what we'll do is we'll use our 3-dimensional coordinate system here, and we'll start putting these things on it just to get a visual. Actually, what I want to do is a point first. So this will be our point R. And that's 5.
Jamie, could I ask a question?
Absolutely.
In the last example, is our vector v supposed to be parallel to RS? Are those parallel?
That is a good question. Yeah, these vectors, the v vector, which is the vector from R to S, and that gray vector called the position vector, those are supposed to be parallel.
Okay.
And you look at the picture like I've drawn, and you may or may not believe that they look parallel. And so that's the benefit of sort of going with a graphing utility, is that maybe you can, once we plot them on here, we can see that they actually are indeed, they're parallel, or at least the plotting utility allows us to believe they are. It might not be very easy to see that they exactly are, because again, we got this sort of perspective problem, right? I mean, if you look at train tracks off in the distance, they look like they intersect, but they're really parallel to each other still. And so you get that kind of problem when you do any sort of plotting of 3 dimensions in a 2-dimensional plane and view it with perspective. But we'll see what happens in this case. You're welcome. Okay, so let's. Oh, I'm going to have to change my max values here. So our x max value will go up to 10. And our min value, I don't think in the x, we didn't get any farther than, actually, I don't need to go to 10. I'll go out to 5. Y, we are only going from 0 out to 5, so that'll be fine. Z is the problem. We want to go -20 up to, in this case, up to 10. Now, when I do this, when I change the scale, this is also going to cause a bit of a problem because I've changed the scale of the vertical axes versus the x and the y axes. And so things like angles and that kind of information is all now skewed. So instead of doing that, maybe I'll pop back and do it after just so you can see what happens. But I'll keep it like this, and I will just bump them all up. So we'll bump them all up maybe just to 15. I don't care if I go off the top of the coordinate system for some of the values. That's fine. I just want to make sure that we are still with perfect cubes. Unit in the X and Y and Z direction are all represented by the same length. Okay, so there's our first point. What's our next point? Our next point is 0, 5, negative 10. That's going to be point S. 0, 5, negative 10. And now we want the vector between those. We've computed the vector. We got it as negative 5, 4, and negative 20. So what I will do is I will add that object in since we've already computed it. This is going to be vector, I'll call it V. And it's negative 5, 4, and negative 20. And you'll notice that when I plot it, it started it from the origin. And so the reason it started it from the origin is because vectors don't have an attachment to a particular point. Vectors are just a magnitude and a direction. So they're free to be positioned wherever we want as long as they point in a particular direction and they have a certain length. I really wanted this to start at, which one? I wanted it to start at R and go to S. So what I can do is I can go into the settings and tell it where the tail is to be. And if I tell it that I want the tail to be, I should be able to just call it S here. Let's just see if this will work. Oh, no, it doesn't. Sorry, I wanted it at R anyway, but that didn't work. So what we're going to do is we're going to type our point in here. We want it to be R, so that's going to be 5, 1, and 10. And there it is. That's the vector we wanted. It goes from R out to S. And the next object we want is actually just the one I already plotted, which was our position vector. And the position vector was really just the same as this one, only it was starting at the origin. So we'll just cut and paste it in there. Okay, and so those are the two vectors we've drawn. And now if we sort of spin them around, we can see they are parallel to each other. One has just been a translation of the other. And what we can do is, you know, you can introduce all sorts of various things if you want to play around with it. You can introduce sliders. And so if I introduce a slider, I can attach the slider variable to the tail. I can put a point in there that has a slider variable in it so that as I move the slider, the tail moves. And we can get things like animations that as I drag the slider around, the vector can move around and we can see how we can translate one to the other. I'll leave you to explore this. I'll probably do some things in later examples, but just so you know that this is just a web tool, freely accessible. You can play around with it, but it's actually quite powerful and you can get some good visualizations to help you think in 3 dimensions. Okay, let's go ahead and continue on. So the only vector with length 0, remember I said a vector has magnitude and direction. What if the magnitude is 0? Well, the only vector with length 0 or magnitude 0 is called the 0 vector. And it is the vector that consists of all zeros as its components. Now the problem with this is, the problem with accepting the 0 vector as a vector is it actually doesn't have a direction then. So saying that a vector is an object with magnitude and direction is somewhat of a lie when we think about the 0 vector. The 0 vector has a magnitude of 0 and no direction. It's sort of the exception to the rule. So in that case, a proper definition of a vector is just in this case, a 3-dimensional vector is just a 3-tuple of numbers, where the first number tells you how far it moves in the x direction, the y value, or the second value is how far it moves in the y direction, and the z component is how far it moves in the z direction. In this case, this moves in no direction. What about the algebraic operation. So I alluded to the fact that with points, we can't add points or subtract points or do any algebra on points, but we can with vectors. And that's the key with working with vectors over points, is that we now can do algebra with them. So the first thing to note is, when are two vectors equal to each other? Well, two vectors, here I've phrased it in terms of 3 dimensions, but it can be for any dimensions. It just changed the number of components we have. Two vectors are equal if each of their components are equal. So if u1 is equal to v1, so the x components are equal, the y components are equal, and the z components are equal. That's what it means to be equal as vectors. We can add two vectors together, and we get the addition by just adding the components. Now, what does that mean geometrically? We're going to want to think about these things geometrically. So what this means is that, we'll do the addition here. I'll just indicate that this picture is relevant to the addition. If I have a vector, let's say u, and I want to add vector v to it, then what I can do is I can just take the vector v and move it through space so that its tail now sits at the tip of u. So I'll just add it onto the end of it. Maybe that's what v looks like. So I slide it up so it lands at the tip of u. And then the resulting vector, which starts where u started and ends at the tip of v after it's been moved, that new vector is what we call the sum of the original two vectors. It's like tacking one onto the end of the other. And I'm going to change my diagram. I'm going to change it ever so slightly. I just want to give a bit of an angle to v. So I'm sorry if you drew yours with horizontal, because I just want to give a bit of an angle there. And the reason I want to give a bit of an angle there is because I want to look at why the components of u plus v are just going to be the sum of the various components of the vectors u and v. So I'm going to draw little right triangles. And what we'll notice is that if I follow these right triangles, that right triangle that's sitting with the u as the hypotenuse, that has x direction u1, and this has y direction u2. And I'm just going to draw the picture in 2 dimensions. The analogous one holds in 3 dimensions, but it's just more complicated to draw. So we're thinking of u as these 2 components. V has a v1 component in the x direction, and this v2 value in the y direction. And now I think about what the green one is. If I draw the right triangle with the green one, I can see that this whole distance here is just the u1 distance plus the v1 distance. And this distance here is the u2 distance plus the v2 distance. And so those are the coordinates, or the components of my vector u plus v. It's got x component u1 plus v1 and y component u2 plus v2. So that's the reason why doing this addition of vectors in this way, component-wise, gives us something that's sort of useful geometrically. We can think of it as sort of tacking one vector onto the end of the other. There is another way to think about the addition of 2 vectors. If you're more prone to thinking about 2 vectors starting at the same place, then we could say, well, okay, if they start at the same place, then what would the sum of the vectors look like? Well, the sum of the vectors we get by just forming the parallelogram. So again, I'll take another copy of the u and the other copy of the v, and I'll just sort of stick them on the ends of each other like this, and that forms a parallelogram. And then the sum is the diagonal of this parallelogram. That's u plus v. So those are 2 ways to visualize the sum. One as sort of a triangle with u and v as 2 sides of the triangle, and then the sum as the third side, or as a parallelogram with the sum as the diagonal across the parallelogram. We call this first one the triangle law, you want to think of it that way, and then this next one parallelogram law. So both of those are used to represent the sum of a triangle, a sum of two vectors. So this is often used as, oh, I want to take the sum. Okay, by the parallelogram law, this is what it looks like as a picture. Okay, you got your parallelogram with the two sides as u and v, and then the sum across the diagonal. So that's our addition. Scalar multiplication. If we have our vector u, and I want to scalar multiply it by something, all it is a vector that points in the same direction, but has been scaled by that factor c. If c is negative, then it just points in the opposite direction. It just flips the direction and makes it go backwards. So that's the pictures we want to think of when we're thinking of these algebraic operations. So the idea is we got vectors, and now we've got operations, algebraic operations we can do on vectors. We can add them, we can multiply scalars to them, changing their lengths and whatnot. So we've got a geometry that we can play with now. A couple of things to note about these algebraic operations and how they relate to the vectors. If I scalar multiply a vector by c, then this just tells me that the length of the vector is, the length of the new vector is just the magnitude of c times the length of the old one. That's what this note part A is saying. The length is very predictable. The length of c times u is just the size of c, size of the number, the magnitude of the number you multiplied by, times the length of the original vector. Two vectors point in the same direction if one is a multiple of the other. That's what this is telling us. And that multiple is positive. So they point in the same direction if one is a positive scalar multiple of the other. And they point in opposite directions if one is a negative scalar multiple of the other. So for example, if this was u, and this is, let's say, negative 2u, and that's maybe our v, then they point in opposite directions because v is a negative multiple of u. It's also twice as long now because the magnitude of that multiple was 2. Okay. Lastly, what about a difference? So you might say, well, we've defined addition. I look above and I say, well, we've defined addition in the algebraic operations up top. We've defined scalar multiplication, but at no place have we defined subtraction of vectors. And that's all right because we can combine addition and scalar multiplication to produce subtraction. And that's what this first line says. It says, how do you make sense of subtraction? Well, u minus v is just the vector u plus -1 times the vector v. So subtraction is just a combination of scalar multiplication and addition. And that turns out to be how we work it out. It's just the difference in their components. What does this look like as a picture? Now, this is one you also want to keep in mind that we're going to be using this quite frequently. If I have a vector u and I have a vector v, what does the difference of them look like? So we could try to draw something similar to the parallelogram law, but in this case, the triangle law is probably the better picture to draw. And so what we do is we just think of the following. We think, I'm trying to figure out how to draw this in my picture. Well, u minus v. Well, that's a vector that when I add it to v, it gives me u. So when I add u minus v, whatever that vector is in terms of the picture, when I add it to v, I've got to produce u. And so that tells me immediately that if I go along v, and then I go along u minus v, I have to end up at the tip of u. And so there it is in the picture. And that's because if I go along these ones, then I have to end up at u because v plus u minus v is equal to u. Okay, so that's where the difference sits. And now you can kind of see, a connection with the previous two examples. u minus v. How do we get that? We get that by taking the tip of u, and then we are, well, maybe I should say it this way. This is a vector that starts at tip of v and ends at tip of u. If you want to think of it that way, you get it by sort of this tip minus tail kind of approach. Okay, so now we've got the ability to combine vectors, work with them in a geometric way. It's a very nice way to work with them because this tells me immediately when I look at a picture like this difference that I get a bunch of results here, that if I start at this point and I go along v and then I go along the green vector, I get u. But it also tells me things like if I started at that gray point and I went along u and then I went backwards along the vector, the green vector, well, the vector in the opposite direction of that green vector is v minus u. So if I went u plus v minus u, I'd get the vector v. So I can sort of just travel around these kinds of pictures, and just by adding the corresponding vectors that each of these corresponds to, I can get results about those vectors. And that's going to help you on one of the additional problems on the homework assignment, which has you looking at properties of parallelograms and diagonals on them, is you just sort of play this game of just moving around the diagram, adding the vectors together that you travel along. Unit vectors. So a unit vector is just a vector that has length 1. So it's got the same direction of the original vector. If we want to think about if I start with a vector A and I want to create a unit vector from it, then I just want a vector in the same direction, but has length 1 now. So I know that I can change the length by multiplying by a scalar. And so what scalar do I multiply by? Well, I just have to divide by the length, and that produces a unit vector. Excuse me. So there's some particular unit vectors that we're going to find very useful, and we've given them names. So two particular unit vectors in two-dimensional space are known as I hat and j hat, and they look like this. I hat is just a vector that points along the x-axis, and j hat's the one that points along the y-axis. And we actually call them that, I hat and j hat, and those are little sort of hat symbols on top of the variable name. You can see I typically write my i's, and this is just sort of to draw your attention to it. I don't write an I like this normally. I write an I like this, kind of like a backwards J, and that's just to avoid any confusion when reading through work. That is that a 1, is that a J, is that an I? I want to avoid all confusion, so I put a little back tail on it. So just so you know that that's how I write these things with handwriting. So for any vector A, we can always write it as a combination of I and j. So if A1 is the x component and A2 is the y component, then we can always write our vector as some multiple of I and some multiple of j. Some multiple of I hat and some multiple of j hat. This tells us how far we've gone in the x direction and then how far up in the y direction. Similarly, for 3 dimensions, we have I hat, j hat, and k hat. And we can take any vector in 3 dimensions and write it as a linear combination of I, j, and k. These are called standard basis vectors. If you've done linear algebra already, then you know all about what a basis vector, what a set of vectors is, which is called a basis, and how we can write any vector in the space as a linear combination of them. If you haven't done linear algebra already, not to worry. The only vectors we're essentially interested with this property are these standard ones. So we're able to write any vector as a combination of i's, j's, and k's. Okay, so let's have a look at some examples. We're in 2 dimensions. Suppose that u is -2, 1, and v is -2, -1. Is it true that u is equal to v? Are these vectors equivalent to each other? Are they the same vector? What do we think?
No.
No, yeah, they're not the same vector because in order for 2 vectors to be equal, where are we here? Back up. There it is. In order for 2 vectors to be equal, all their components have to be equal. So this tells us that they are not equal. They do not have the same y component. Let's do a few calculations. So u plus v is -2, 1 plus -2, -1, and that's equal to -4, 0. What's 2 times u? That's 2 times -2, 1, which is -4, -4, comma 2. Oh, sorry, I missed that. That was, oh no, there is a comma there. Sorry, it was the next one. Oh, now we're going to do -3v. I'm getting ahead of myself here. -3v, that's -3 times -2, -1, and that's 6 and 3. And then lastly, we want to do 2u minus 3v, and that is equal to, well, we've already worked out 2u, and we've already worked out -3v, and so our result is 2 and 5. Okay. Hopefully I haven't made any mistakes there. So you notice that in order to do this linear combination 2u minus 3v, we do each of the individual vectors first and then add their corresponding results. Let's look at another example. This one involves magnitudes now. So I want to know what the magnitude is of a plus b. So I first work out what a plus b is. That's -3, 6, and 5. And now I got to work out the magnitude of that. That's the square root of -3 squared plus 6 squared plus 5 squared. And that's equal to square root of 9 plus 36 plus 25. And what is that? That's 50, 61 plus 9 is 70. So that looks to be about root 70. The next one we can do is -3 times a, the magnitude of that. And here is where we want to just pause and think, do I want to multiply by -3 through a and then sum all the squares of those things? Well, that would make the numbers get a lot bigger faster, and it would be a little bit easier to just realize that the length of -3a is really just the length of a multiplied by the magnitude of the scalar that I'm using. And in this case, that's 3 times the length of a. And so that's 3 times the square root of 2 squared plus 3 squared plus 5 squared. Or 3 times the square root of 4 plus 9 plus 25, which is 3 times root 38. And lastly, we want to work out what 2a minus 3b is. So that's 2 times 2, 3, 5, and minus 3 times -5, 3, 0. So that's going to be 4, 6, 10, plus 15, -9, and 0. So this is 19, -3, and 10. So there is our linear combination of the a's and the b's. All right. It was just a little bit of sample play with the arithmetic of vectors or the algebra of vectors. One last one is just now bringing these ij's and k's into the picture. So if a is negative 2i hat plus 3j hat plus 5k hat, and b is that vector given, write the difference in terms of ij's and k's. Now the point here is that using ij's and k's is just a way to avoid using the angle bracket notation. Rather than using commas and angle brackets, we're using ij's and k's and sums. That's really the only difference. Is just the choice of notation just tells you whether you're going to be working components wise with angle bracket notation, or whether you're just going to be separating the components off using these variables ij's and k's. So for us, if we go ahead and work out the difference, then what we can do is just say, well, it's going to be that minus negative 3i hat minus 3j hat plus 5k hat. So that's, now I go ahead and I work out what the individual values are in front of each of these unit vectors. So the I hat, there's a negative 2 and then a minus 3. So that's a 3 minus 2. And in front of the j, there's a 3 plus 3. And in front of the k, there's a 5 minus a 5. So this gives us a I hat plus 6j hat plus 0k hat. And the nice thing about this notation is that we don't really need to keep that 0k hat. 0 times anything is 0, and then added to anything is just whatever you're adding it to. So I can get rid of that 0k hat, and I'm just left with this expression, I plus 6j hat, I hat plus 6j hat. And that's part of the nice bit of using this notation, is that we don't have to have that extra component, comma 0 closing angle bracket. We don't have to include the zeros as our components, because we can see that they've got to be 0 since the k hat is missing here. So it simplifies our notation just a little bit in the case of some components being 0. Okay, so that's really all I want to introduce in terms of vectors and their arithmetic. The properties that we've covered, and then some that we haven't covered, but just follow from the basic principles of arithmetic that we all know, are listed here. So for example, part A says that it doesn't matter which order you add two vectors in, whether you do u plus v or v plus u, you're going to get the same result. Adding the 0 vector to any vector just results in the original vector. So u plus 0 is u. Scalar multiplying by 0 produces the 0 vector. And then we've got some, what happens if we scalar multiply by a and b? If we multiply a and b together first and then scalar multiply by u, that's the same as scalar multiplying u by either a and b, a or b, and then multiplying by the remaining one. So that's that property D. We got a distributive property that u can distribute across a sum. But we also have another distributive property down here that says a scalar can distribute across a sum. So these are two kinds of distributive properties: vector distributing across the sum of scalars, and a scalar distributing across a sum of vectors. And we've got some other ones there that it doesn't matter when you're adding 3 vectors together. So this is F. When you're adding 3 vectors together, it doesn't matter which 2 you add first. You can add u and v first, or v and w first. It doesn't matter. And then add the third one after. U plus negative u is 0, and scalar multiplying by 1 leaves the vector unchanged. So just all basic properties that just follow from the properties of arithmetic that we all know and love. Okay, so that's it for the basics of the geometry of vectors and how to work with them algebraically. I'm just going to take a couple of minutes now to introduce the dot product, and then we'll go a little bit more formally through it next day and do a lot more examples, but I just want to introduce the dot product so that you can start thinking about it over the weekend as well. This dot product is a way of multiplying vectors together. So one of the things that we didn't talk about in the last lecture, or the last section, was given two vectors, we can add them. Given a scalar and a vector, we can multiply them. But at no point did I talk about, what if you have two vectors? Is there a way to multiply two vectors? Well, it turns out there isn't a way to multiply two vectors per se, in the sense that there's a unique way to do this. It all depends on what you want to achieve. So there's a couple of ways you could multiply vectors. You could take two vectors and you could form a scalar from them. That's what's known as a dot product. Two vectors in, scalar comes out. Or you could take two vectors and produce a vector from them. That's known as the cross product. And it turns out that that only works in 3 dimensions. Higher dimensions, we don't really have a cross product. There are other things that can kind of substitute for it, but we don't really have a way to multiply vectors in higher dimensions. So the first thing we're going to look at here, though, is the dot product. Two vectors in, scalar comes out. What does that scalar tell us about the original two vectors and their geometry? So let's find, first of all, the motivating problem is find the angle between these two vectors. So we got two vectors in space, wherever they are, A and B. And what I'd like to do is I'd like to find the angle between them. So what's the angle between them? How do I find that? Turns out that it's related to the dot product, which we're defining here. The dot product of two vectors is obtained by just taking the product of their x components, the product of their y components, the product of their z components, and adding them up. So for example, if I want to find the dot product of these two vectors, then it's 5 times -3, the product of their x components, plus 7 times 4, plus 0 times 2. Or in other words, -15 plus 28 plus 0, or 13. Okay, that's what the dot product is. You might be thinking, well, big deal. What does 13 even tell you? Well, it turns out that this value that we get out in the end tells us something about the geometry of the two. In fact, what it's really telling us is how much they point in the same direction. Now, that's sort of clouded by the fact that each vector A and B has a magnitude. And so the higher the magnitude of A and the higher the magnitude of B is, so the longer those vectors are, conceivably the bigger the dot product is. So it's sort of clouded by these extra scalars. But if we were to think about it this way, suppose I was to take a unit vector in the same direction as A and a unit vector in the same direction as B, and then take their dot product, that number that I get out is telling me in some sense how much those two vectors are pointing in the same direction. How much are they pointing in the same direction? And what we get is a bunch of properties now. Much like we had those algebraic properties of sums and differences, we now get these properties for the dot products as well. The dot product of a vector with itself is the square of its magnitude. The dot product of a vector A and a vector B, doesn't matter which order you take it in, just because of the fact that you're just multiplying components, so it doesn't matter. Scalar multiplication or multiplication of two numbers doesn't matter which order you do them in. We got a distributive property of the dot product that if I was to take A dotted with a sum, I could just distribute it across and get the individual dot products and add them up. Scalar multiplying a vector and then dotting it with another vector. It doesn't matter when you do the scale. You can do it on either vector A or vector B first before you take the dot product, or you can just scalar multiply the result. That's what that middle term is saying. And lastly, the dot product of any vector with A is 0. So those are some basic properties that just follow right from the definition and a bit of arithmetic or algebra. What we want to do, and I'm just going to mention it now and then we will prove this next day, is we're going to show that there is a geometric interpretation of the dot product. So it's a kind of funny little multiplication. Multiply the x components, the y and the z components, and then add up all the results. And what do you get? It turns out that the value you get is equivalent to multiplying the two lengths together. As I said, it was sort of skewed by these lengths. That number 13 had the lengths of each of the vectors involved, but it somehow measured the direction that they were pointing in, at least how much they point in the same direction. And that is precisely stated as it's the cosine of the angle between them. So A dot B is the magnitude of A times the magnitude of B times the cosine of the angle between them. So if we want to think about when is this dot product as big as possible, well, cosine is a number between 0 and 1. I'm assuming theta is an acute angle, so between 0 and pi by 2. So I don't have to worry about negative cosine values. So it's between 0 and 1. Cosine is as big as possible when the angle is 0. That means when they're pointing in the same direction. So the dot product is as big as possible when the vectors are pointing in the same direction. And then as they stop pointing in the same direction, sorry, let me get a darker background here, maybe on my face. As they start not pointing in the same direction, the angle gets bigger, closer to pi by 2. Cosine is dropping in value, so the dot product's value is getting smaller and smaller and smaller. So the dot product is a measure of how much they point in the same direction. We're going to prove this result next day, and it just falls from the Pythagorean theorem for right triangles. So that's it for today's lecture. I'm going to hit the stop record, and you can ask some questions if you want.